The next speaker is familiar to you because it's me. I'm, to read my own bio, I'm the sales system director at Breakthrough Starshot and the president of Microwave Sciences in what? in Lafayette, California. I have had a long career in this field of about half a century, and my primary interests include high-power microwave systems and millimeter wave systems, from conceptual design to hardware to experiments. The microwave source physics, electromagnetic power beaming for space propulsion, experimental intense particle beams, and plasma physics, which is where I started on the fusion program when it was going to be solved within a couple of decades, 50 years ago. I'm co-author of the widely known textbook High Power Microwaves, now in its third edition. I got a PhD from UC San Diego when it was called UC La Jolla, which was 50 odd years ago, and I'm a fellow of the IEEE, and I'm thinking about retiring now for the third time. Now, the talk. I thought of making this a good news, bad news talk, but then I realized there's no good news, so I'll just talk about the realities. Sailships for Starshot. I'm not going to talk about payloads very much, except where it's located, because Dave Messerschmitt is going to talk about the real problem, which is how do we get the data back. The essence of the problem is in the next slide. We know that if you look at all the other methods, antimatter, the ramjets, any of the fusion rockets, they're really just not practical in this era for interstellar. The sails are the only thing that make any sense, if they make sense. Next slide. Here are the major problems. What's the shape of the sail? Can it be stable on the beam? I think this is really fundamental, because if you can't, it's all over. It's all over in seconds. The sail dynamics, which is separate from stability, because dynamical questions can interrupt stability and also influence things like the survivability of the sail itself. Therefore, a key factor, very important, is sail materials, which will be a major focus of Starshot. And then, of course, there's the question of how do you test these materials, the dynamics, the stability? How do you actually know whether this can happen? And that gets into laboratory work, which is what I like to talk about because I'm an experimentalist. The fundamental issue, if you want to take away note, the fundamental issue is that these fundamental engineering issues are interrelated and unresolved at this time. But it's early days. Now, next slide is the technical landscape. Okay, everything comes together on the sail. The laser hits it, the payload's in it. It has to do all the heavy lifting in the sense of not acceleration, but getting there, has to survive, has to take the data, has to send it back. So it's all the issues converge on the sail, and therefore the challenges are interacting with each other. The challenges of the whole system interact through the sail. That's my point of view anyway. Stability is influenced by, and I list the things here, so the shape, all the other stuff I mentioned, the beam shape, they all influence whether stability can occur. The material aspects, primarily the optical aspects, are listed here as they were in Kevin's talk. And there are other aspects not mentioned, typically tensile strength, but of course aerial mass density, the fact that this is incredibly diaphanous material that's just 100 nanometers thick, is a very demanding material requirement. And the laser system interacts in many ways that Bob Fugate just told you. And in particular, I want to mention something we don't tend to think about, the pointing error, which Al Jackson will talk about this afternoon, and well as the pointing jitter and the noise spectrum that occurs on the sail due to the laser, but also due to the fluctuations in dynamics of the sail itself. I'll talk about all these matters. Next. Sail shapes. We have several suggestions. None of them are the standard. Next. This is the Conical Beamrider that my brother and I tested the stability of some 15, 16 years ago. And we found that this was, within a limited regime, which I will show you, stable on a Gaussian beam in the laboratory. I'm talking about mostly about experiments here. Next slide. It's stable because, if you can see here, if you just follow the arrows, if the sail is centered on the beam and then moves off center, you get a restoring force, a net sideways force. It tends to restore it to its original position. We verified that in the laboratory and measured the restoring force. So it does happen within a limited regime. That's the experimental result. That is the single experimental result on beam stability, on sail stability, that's ever been done. The first, and thus far the last, such experiment. However, you can also spin the sail to stabilize it against pitch and yaw. Next. Now, the whole idea of the conical sail basically is, you think about it this way, it's like a parachute. The parachute is really stable because the center of force is the air hitting the parachute, and the center of mass is the payload, the cargo or the person underneath. The center of force of being above the center of mass is a stable configuration. The other way around is what rockets are. Rockets have the center of mass over the center of force, and they spend a lot of time trying to, or they really quickly, trying to keep that thing stable until they can get up to higher speeds. And we've seen lots of pinwheel rocket videos, right, where it doesn't work that way. Okay, so you want to have that distribution. The idea of this kind of sail is to have that distribution. Next. So you get this kind of image, which you've now seen 3 or 4 times. Now, notice that boom that connects the two. Now, this is just a concept, okay? That boom is a mechanical element, which, is it rigid? Is it flexible? Well, whatever it is, it's got its own dynamics. And therefore, you've got essentially 3 objects, not 1 object in the sail. The sail that accepts the force, the payload that's you're trying to deliver, and the thing that connects them. Perhaps the most obvious thing is to integrate the two and not have anything to any kind of connection. However, there are difficulties at that. Here are some shapes that have been looked at the University of New Mexico in simulations done in the early part of this century. Cones and things like cones, and like in particular, this marvelous bottom left thing, which is kind of like a chevron outline, and it's reasonably stable, actually. Those are the kinds of things that have been looked at and have found to have limited stable regimes. There is no consensus on the most suitable geometry for sail stability. I want to keep making this point. We do not know these answers. There's the sphere, inverted pyramids, so to speak, and things of that sort. Next. I'm going to now go through the stability question as it relates to shape. Next. To continue to talk about this conical sail with the payload hanging below it. Work was done by Emil Shamaloglu's group at University of New Mexico over a number of years, finishing about 10 years ago, that ran simulations on what these kinds of devices would do in real distributions. We took a Gaussian beam and saw and ran the movies. I won't show you the movies. And a lot of them are unstable. A lot of configurations are unstable. Next slide. This shows you, as you can see, the red up here is the stable domain. This is basically the height versus the width, the aspect ratio of the sail. This is the stable regime up here, and all the rest is unstable. We mapped all these and basically found that the included angle, the angle down here underneath, has to be about 120 degrees, which means the angle of the sail from the horizontal is about 30 on each side, 30 degrees. And the beam width has to be approximately the sail diameter in order to have a good restoring force. It's also required, if you're going to have any kind of efficiency in delivering the beam to the sail. If the beam is much bigger than the sail, you have some stability, but on the other hand, you're wasting most of the beam, which we will see occurs in other designs as well. Next. The Popova group recently published a calculation of the stability of such sails on a laser beam and came to the following conclusion. The stability occurs if, and I'm going to introduce some terms here, if L is the distance between the center of mass of the system and where the payload is hanging, it has to be larger than the sail diameter. That distance has to be larger, and therefore, the distance from the sail to the center of mass is larger than the sail radius or sail diameter, and that means it's pretty far below the sail. It's hanging out there. You can't do what I'd like to do and put the payload as a distributed payload around the rim. Why would you like to do that? First, it's symmetric. First, there's nothing. Second, there's nothing hanging down. And third, it gives you it disperses the payload from damage due to interstellar dust and particles. You'd like all of those. Doesn't look like it's going to work, though. So that's some more bad news. Next. Now, Avi Loeb and especially Zach Manchester introduced about a year ago the idea of a spherical sail. It's a nice theoretical idea. Spheres are beautiful. And they've done a lot of work on it. I'm going to run through what they have discovered. Next. The spherical sail has the beauty of symmetry, and so if you see a light ray here, bounces off, produces a force inward, and would be just the same on the other side because it's a beautiful sphere. That's the good news. The bad news is that the sail will never be a beautiful sphere. This beautiful sphere is this sort of thing, right? And that might be, in fact, be what our early experimental objects will look like. We'll just buy inflatable, helium balloons and run them in a laboratory. Next slide. They introduced stability into this, pretty good stability, into this configuration by putting the spherical sail in a hollowed out beam. And basically, think of it this way. It's like a light pipe. The laser beam is a light pipe. It's largely hollow, and the sail just bounces off the walls. That's one way to think about it. That's the good news. Bad news is that most of the beam doesn't hit the sail. In the calculation by Zach and Avi, 80% of the beam didn't touch the sail. Well, all you have to do is make 5 times as much power, Bob. Just a factor of 5.
Or make the beam smaller.
Or make the beam smaller by making the aperture larger. I'd recommend the latter, actually. We'll talk about that later. So I talked to Zach about this, and he said, we've looked at that, although we didn't put it in the paper. I like that. But we think we could get it down to maybe 70 or 60% loss, which means only factors of 2 or 3 or something in the laser power. And it would be stable and bounce around in the beam. And that's maybe something of good news. Next. The problem is, what this is a potential well that the sail is sitting in. And it bounces around in the well. As you all know, we live in a potential well called gravity, and every day when we get up and get out of bed, we're trying to dig out of that well. Well, the potential well in these kind of configurations isn't that hard to get out of, unfortunately, because it's weak. Next. So what are we going to work on? What are we going to do about this stability question? We've got to optimize the sail shape and the beam profile together to develop a computationally tractable stability metric, to use a lot of jargon, and to populate the trade space of shape and of both beam and sail into a library of configurations that will work. That's an optimistic statement. We don't know that there are configurations that are really going to work and be attractive, but at least we know there are some that will work that are not particularly attractive. Next. And then there's the question of dynamics, seldom mentioned. In fact, there's essentially no literature on this. Next. Avi and Zach, in the 2nd or 3rd edition of their paper, noted that you're going to get noise in the beam due to phasing errors and in the laser beam, and you're going to get air turbulence, and you're going to get oscillations in the sail material itself. Remember, this is a diaphanous object. It is very thin. You might be able to see through it, as you could with the sails that we flew a long time ago. And they're going to get distorted by this acceleration. They're being pushed around. They've got forces applied to them. They're going to be distorted. And that's going to produce a noise spectrum in the acoustics of the material itself, and therefore you got to worry about noise. So they did a calculation in which they induced phase errors in the beam and studied the motion of the sail. And this result is pretty good. It shows that if on the left you see something with no noise, and you see here the object, the sail, accelerating up to velocity, and this is the bounce of this sail in essentially something like a 1 meter diameter sail, and it isn't moving very much, just a few inches side to side. You introduce noise at the level they guessed, because we don't know the noise level, but they made what they thought was a reasonable estimate of noise, and they found that it still stayed stable. We need to explore how much noise we can accept, because that's another criteria to apply to the material of the sail and to the beam itself, the beam profile. So noise is something we don't tend to mention, but it's very important, but it's not the only dynamics problem. There's also vibrational modes of the rotating sail, assuming that it's rotating and spinning. And I'll show you in a minute that it probably certainly will be spinning, even because we wanted it to, or because nature made it spin. And these vibrational modes produce acoustic signals, vibrations in the sail itself. This is a planar sail, and it shows you the vibrational modes. And there's been a lot of work by Giancarlo Genta, who will be with us later today or tomorrow, on this question of whether or not these modes would go unstable under the acceleration. And that's an outstanding problem. So we have vibrational modes, we have the noise in the system, and these are all dynamics problems, but it's not the only dynamics problem. Next. Here's a very nice diagram that shows what happens if it's a non-uniform situation, which it will be. Suppose the beam profile is not uniform. You end up with a spinning sail. This is for the case of a spherical sail. Suppose the sail, well, come down here. Suppose it's not rigid, and it won't be rigid. Why? Because it's being pressed on. This spherical sail is being hit by an acceleration, and it's going to become more oblate, or maybe prolate, and it's going to have vibrational modes. And as this diagram shows, you would expect this would lead to a spin of the sail. And if the mass distribution is not really uniform, for example, the payload gets off center, then you can also see the sail start to tumble. So the beauty of the symmetry of the sail is destroyed by the dynamics. Yes. Truth and beauty are not actually identical. Next slide. We have another problem. If it spins, what happens to it? Well, first of all, if you're coupling a lot of energy into this, and if some of that energy is coupling into rotational motion, you're going to have to worry about the tensile stress in the material itself. And in fact, the silicon dioxide that Kevin introduced in his talk has, as you can see down here, very low tensile strength, whereas a lot of other materials have high tensile strength. But therefore, it is possible that this diaphanous sail would essentially be torn apart by spin, by rotation. That's the bad news. You might think that the good news is that it might survive that. But that's not so good either. Next slide. I'm going to talk to this in a minute. Here's what can happen. The sail starts spinning. The acceleration goes off. You're left with a final state where the sail is spinning. Do you know how much spin it's got? From Doppler shifts, from god-awful distance away, halfway to Mars, as we heard this morning? Maybe, maybe not. What do you do about it? You can't, the spacecraft needs to know where it is. How is it going to do that if it's spinning and the payload's on the inside? You have to unfold the sail. You have to be able to orient it, and you're probably going to have to control that spin or zero it out in order to be able to navigate. And so that means you got to reconfigure, I'm talking here about the spherical sail, reconfigure the sail into something that's not spherical so you can expose the payload. And the payload is going to have to find its way around. And it's going to have to deal with the spin, which will probably be happening. So even if you survive acceleration and spin up, you've still got a deployment problem on the way to Alpha Centauri. Now, what do we do about all this? Well, we need a computational code that will deal with all this, or say a family of codes, gradually upgrading into higher and higher levels of resolution and accuracy, and included effects. They would have to include, as you can see here, this long laundry list of stuff: implications of the beam profile, the beam jitter, the sail shape, the spin, the flexibility and material properties, tensile stresses, deformations, and now we go to the next slide to get the rest of it. So we have to include multiple internal reflections if we're not talking if we're talking about something like a cone which can reflect internally, if it's greater than 30 degrees incidence. Reflection absorption as a function of angle of incidence, which is indeed quite possible with advanced materials. We can tailor that, the acceleration at a given place because of the angle of incidence of the photons on it. We have to take care of, we have to understand and vibrational modes, transient and steady state. I mean, the usual analysis is entirely steady state. We have to look at the transient. We have to look at the transients on the time scale that will occur. And we don't really know how high the frequencies of the transients will be at this time, the noise spectrum, the vibrational modes. And we have to take into account the fact that the sail will likely be spinning either deliberately or inadvertently. My brother and I did some experiments about 12 or 13 years ago in which we showed that you can, and this is not a surprise in physics, you can spin a material object using a polarized electromagnetic wave. We showed that we could take a cone or any other object and spin it with a microwave beam at a distance, so you can control spin. But controlling them over these distances is difficult, and the other problem is that this control of spin, think of it this way: the light wave is spinning the object, I should say the electromagnetic wave, is spinning the object with a lever arm that's the wavelength. If you're using lasers, the wavelength is very short, you have very little leverage. So you're going to have to do it with lower frequencies. And if you do that, say go to millimeter waves, you have a bigger lever arm and your spin efficiency is much better. But on the other hand, your beam is wider. So that's something we might be able to do, but controlling spin at a distance is going to be an issue that's not recognized in the literature of this kind of mission. But I think it might come into mission planning, and I don't think there are any easy answers. So we also, by the way, besides computational studies, we need analytic descriptions of linear, nonlinear stability problem in 3 dimensions. There aren't any three-dimensional analytic models, and the analytic models tend to be gross oversimplifications of the kind of factors I'm just telling you about. Next slide. Sail materials. I wondered about how much material to put in here about sales materials, no pun intended. And I decided to go minimalist because there's a huge category of possible materials, and they all have their advantages and disadvantages. Next slide. Photonic absorption, okay? We want to avoid it, although Kevin pointed out that maybe it's not so bad, but on the other hand, we can't melt the sail. So we have to keep it down. We might be able to accept some substantial transmission of the beam, but we can't accept much absorption, like on 10⁻⁴, 10⁻⁵. The sail experiments I'll show you in a minute, we did with an absorption of 10%. But carbon doesn't melt very easily, so we got away with it. The sail material has to avoid damage using sufficient photonic absorption. And so you might use something like silicon dioxide, and you might use high refractive, that is ultra low absorption material or high refractive index materials, and there's a list of those materials there. We don't know what the right solution is. But basically, we've got to have little absorption, or all we'll be doing is sending a melted object to the stars. Next slide. Here are several geometries of materials. You can see there's basically a plane, a group of planes, a plane with holes through it, a plane with studs sticking out of it. These are advanced materials that are being studied, such as metamaterials and photonic crystals. It's tremendous advances being made in this area. We can expect a lot of progress. And I'll show you an example of something that is attractive. This is a brief, yes, good news slide, okay? Here is a perfect metamaterial. Perfect. Here's what it looks like, these silicon cubes, okay, mounted on a silicon dioxide background. And if you put, say, a laser at about 1 micron onto this, you get this kind of curve. Next slide. Here's the curve seen larger. Up here we see, what's the reflectivity? It's totally reflective. What's the transmissivity out here in this region? Forget about it. Hardly nothing comes through. Absorptivity, 10 to the minus 5. So this material is perfect. It's great. That's the good news. The bad news is it's too heavy, a lot too heavy. And so it doesn't meet the spec, although you can certainly do experiments with it. I mean, we don't have to have the last answer in the first experiment. But those are the kind of problems that we face. We know how to make materials that would meet all the optical requirements. We don't know how to meet the mass requirement. And then there's the tensile strength. And then, oh, by the way, it's a long list. I showed it to you. So there are a lot of issues in the materials, and we don't know the answers. But we will be holding some workshops on the materials in the very near future, this month. And there will be an RFP in this area released in the first quarter of next year, of all the areas I'm talking about having to do with the sail. Next slide. So in materials development, we're going to have to, I just said all these things basically, we're going to have to survey all the materials, narrow it down to a few to fab and do lab tests on for the properties I've just mentioned. Construct what we call a mini wafer prototype of about that size, okay? Test them in a facility first to make sure the properties are right, but also to see whether or not they can ride a beam stably and whether they can survive acceleration. And that brings me to the next topic. How do you test all of this? How do you test the materials, the dynamics and stability? I'm an advocate in the program that we have to do this soon. Why? Number one, it's an important problem. Number two, we can actually do this soon. We don't need to invent anything to do this, start doing these such tests. Number three, we've already done experiments in this, so we know how to do it. And number four, if we don't get the right answer, the program is dead. Those are my arguments. Now let's go back in time, as old men like myself tend to do, and talk about what we know about doing testing of dynamics and stability. Next slide. Way back a long time ago, about 2000, in NASA-funded work conducted at JPL, I led a group that did studies of this area. I want to show you that in order to show you what the elements of testing are like. This is going to be the experimental problem of the Starshot discussion, okay? You have to have a beamer. In this case, it was a 10 kilowatt klystron in X-band, which we irradiated into a vacuum chamber. Next slide. It came out like this, out of a waveguide, vertically oriented. Sail was brought down on a carbon fiber, so it's a 1D experiment. The sail goes up and down the fiber with a little bit at the end to stop it from falling off. All of it made out of carbon. The wavelength is given here, 3 centimeters. We fired, we set up the experiment by heating up the sail and driving off all the volatiles for some time. Pumped down to a really good low vacuum pressure because you don't want to heat up carbon in air because it'll burn. None of the sails burned. On the other hand, is a long turnaround time to evacuate the chamber. And then we use power levels from 2 to 10 kilowatts to accelerate sails. Next slide. This is the chamber. You see there the waveguide coming in from below. The sail will sits up here. The microwave beam accelerates the sail upward. This is a carbon absorbing surface to capture all the microwaves and make sure we didn't get reflected waves and things like that. That all worked very well. And it's a big chamber. You can walk around in it, which means it takes a long time to pump down. So what we did is set up, next slide, this geometry, and we shot sails into the air. It worked. Of course, it took about a week to get it to work, but and we didn't have a high shot rate, but these are the first videos of sails in flight, and thus far they're the only ones. We have not, this is the first and only set of experiments that actually has flown sails. Here, for example, on the right, going from top to bottom, the framing interval on this video is 30 milliseconds, 1/33rd of a second. The beam is not on in the first, it's on in the second. It lights up because it's absorbing 10% of the power. In the next frame, it is beginning to move and it's getting hotter, and in the next frame, it's gone. What does this tell you? First, that sails work. We reached accelerations of 13 Gs, but the velocities were only about 3 meters a second because it hit the ceiling and ran out of the beam. But it also tells you that you're going to have to photograph the motion of the sail all over the place because you don't know where it's going to go, especially in stability experiments. You've got to know where it goes. And if you make, as some people advocate, make the sail a millimeter in size, then you've got to be able to resolve a millimeter everywhere in that vacuum chamber. And therefore, you have a whole lot of diagnostics. So I favor seeing things that are more reasonable size. It also helps to be able to find them later. Next slide. So what do we need? We need a sail flight chamber for acceleration and stability, a free-flying sail experiment, free, not bound, not a 1D experiment, although you'll always start that way. But you'll go to about on the order of tens of Gs in these experiments. But the key thing is you need to diagnose the devil out of it. You have to measure the velocity, the position, the velocity vectors, to be able to deduce the instantaneous acceleration. You have to know, of course, know where the sail is and what its orientation is. You need a lot of imagery. You need a lot of imagery in the IR to see how hot it's getting. You need to measure the temperatures. And you need to basically track what's going on in real time. So it's a very diagnostic intensive facility. But all these diagnostics exist. And I'll mention one that people never think about. You need an RGA, a residual gas analyzer, to tell you what did you boil off of the sail, which you can detect. And we did that in our experiments. And we found it was, guess what? Carbon dioxide. Because there was an oxidation of some of the carbon in the sail had occurred. And when you get hot enough, you boil it right out of the lattice. That's about above 2,000 degrees. We went up to close to 3,000 degrees. We use carbon because carbon has no liquid phase. It goes from a solid to a gas, but it does that at about 3,200 degrees, and so we just got away with it, basically. That was one of the arguments we made that we could do this experiment, is that the carbon nanotubes had been brought to the point where we could make them so light that we could sail them. Next slide. So we need a test facility to do all this work in. We like to talk about models, but models are just a concept about nature. If you want to know what happens, you have to ask nature, not tell it. So the experimental capability is to test sails, all the aspects I've mentioned here, from stability and dynamics and materials. We've got to be able to test this, and we've got to do it in an integrated way with the codes so that they can talk to each other and we can learn. Experimental physics is like walking on two legs. One leg is theory, the other leg is experiment. If you have only one leg, you're hopping. You're not getting out, you're not moving very far. So we've got to measure all these components I just mentioned, good imagery, and that's basically fundamentally what we have to do in a facility. Next. Oh, one thing we were thinking of doing in a facility, especially in acceleration, which is the horizontal tube concept that Kevin talked about. We're going to have to get up to high velocities. The way to do that is get high acceleration. The way to do that is to try to recycle the photons. This is a crude diagram, that is, it's mine, which says you inject into a conducting container a sail that is located here at this end. You inject some kind of electromagnetic beam, accelerate the sail, but the sail is a reflector, so it bounces back and back and forth and back and forth. Every time it hits the sail, you get acceleration. If you could get 10 times as much, or 10 times the reflections, a reflection of 10, that is, you can reduce the length of the experiment by a factor of 3. It goes as a square root. If you can get 100, you can reduce that multi-kilometer tunnel by an order of magnitude. There are big economies in that, and so we need to investigate that pretty soon. And that's an idea that Jeff Landis proposed quite a few years ago with Metzger. Next slide. Oh, by the way, we need data acquisition, analysis, diagnostic calibration, vacuum equipment, specialized tools, a machine shop, conference rooms, restrooms, cafes. Facilities take a time to design, they take a time to build. Codes can be developed quickly, but facilities you have to start pretty early if you're going to be ready to have codes and experiments work together in a synergistic way. Next slide. So a friend of mine made up a picture of this sort of thing, which just shows a concept that you have a vertical stability thing here, experiment, a chamber, with tilt fixtures so you can take it down, reassemble and put it back up. You need beamer sources and controls here for whatever wavelength you're trying to use. And then you have an expandable horizontal chamber, which you start with on the order of, you start with perhaps a 5-meter vertical, which would be about the height of this ceiling for stability experiments. But when you go to the horizontal, you're probably going to have to start at something like 10 meters and be able to have a facility that you can expand out to 100 meters at least as an initial capability. So these facilities have to be thought about ahead of time because they take a while to build. Next. At last, the summary. No consensus has been reached on the most suitable geometry for sail design. Sail material choices abound, but the requirements are quite daunting because it has to meet requirements, photonic requirements. It has to meet strength requirements. It has, and in fact, I gave you a whole list of the requirements. It's a very daunting thing, and we're going to have to work on it very hard to get the right materials. Now, let me point out that you don't have to have the perfect material to do initial experiments. You can do stability and dynamics experiments with things that are not going to make it to prime time. And you can also use wavelengths that are not lasers too, because other sources like millimeter waves are orders of magnitude cheaper and more available. And finally, we've got to develop simulation codes, which I outlined, beam-driven sail test facilities. But, final optimistic note, we are hopeful that we can deal with these questions, and the first step in dealing with them is to recognize all of them, not just some of them. Thank you. Surely there are no questions. No question?
Since you're studying the geometrical shapes from a theoretical point of view, and since you're using photons, there's only one idealized shape that's going to have like a uniform phase space density, keeping uniform phase space density, and that's the Winston cone. And have you studied...
What was the question?
So have you studied the Winston cone as a theorized shape, since it keeps... You don't have the reflecting photons. In a conical, reflecting photons are going to fight against each other, whereas in a Winston cone, the shape is optimized to keep phase space density of the laser beam going to phase space, uniform phase space density.
Thank you for your brief question. I'll give you a brief answer. No. we haven't looked at it, actually. Perhaps I'm going to write that down, and I'll talk to you later. Yes, please.
You didn't actually mention one of the problems I think it's going to be your dominant
Oh,
problem.
good. You think you have a question we haven't thought of?
Yes.
Good. Tell me.
Okay, I'm used to aiming proton and antiproton beams to an accuracy of 30 microns over 4 miles. So I have a little understanding of what you're trying to do here. The dynamics, when you have a potential well and you have an oscillation with that potential well, you need to understand the amplitude of the oscillation, and that's driven by the power spectrum of the noise around in the line width of that resonant frequency. How do you know what phase you are in that oscillation when you stop the laser? And so therefore you know you're going to hit what, one light minute within 4 light years.
Thank you for your question. That's a really good question. Here's a long answer. I think one of the key fundamental problems, which you've just pointed out by implication, is that we don't know quite how to find out the final state of the sail after the acceleration. Now, Al Jackson, this afternoon, in the first talk, is going to tell us that what the limits are on how precise we need to know where that is and where it's going. And it's daunting. The dominant term in that whole question is not where is Alpha Centauri. We will find that out better and better. It's where our sail is and where it's going. And having an understanding of just what we did is going to be very important, both from operational aspects, but with just dauntingly hard in diagnostics. And so I think that is, in fact, a key question that's hardly ever mentioned at all. And you'll hear about it this afternoon.
Second issue, the light tube with the reflecting the light back and forth.
Yeah,
That
light
itself
height,
is
yeah.
a source of instability, because the angle of the reflected light will drive other angles in the intensity of the profile against the sail.
Oh, I hadn't thought about that. Bob, we'll have to think about that. Yeah. Thank you.